Welcome to the deep dive. We take complex source material, dig in, and, well, hopefully pull out the key knowledge you can really use.
That's the plan.
Today, we're wading into freshwater aquatics, specifically looking at something you usually find in saltwater tanks, dried coral rock, but used in freshwater. It's interesting.
It is, and our source for this is Notes on Fishkeeping, Part 61. Our mission, really, is to quickly evaluate this technique documented there, understand the claims, but also, crucially, how the environment changes things.
Right, because the core question here is kind of odd. The author of these notes, Ang, saw something in fish stores. Most use standard stuff, sponge filters, that sort of thing.
Yeah, the tried and true methods.
Exactly. But this one store was using sponge filters plus dried coral rock in freshwater tanks. So you immediately think, why? Why the extra step? Is it redundant? Or is there some hidden benefit?
And that's the hook, isn't it? That combination. It suggests maybe the standard filters aren't covering everything these store owners want. I mean, they're running a business indoors, controlled conditions. They want healthy fish, low maintenance. If they're adding something extra, something maybe a bit specialized.
They must think it's doing something important.
Precisely. There must be a specific performance boost they're after.
Which is exactly what got Ang thinking, apparently. The notes detail this observation. Sponge filters everywhere. Pretty standard.
Board course,
But the added dried coral rock in almost every freshwater tank, that was unique to this place.
And Ang recognized, okay, maybe this combo is why they're successful or part of it. But instead of just copying the store setup,
They changed the game.
they did. They decided to test the coral rock, but in a totally different, much tougher setting. An outdoor pond.
And that contrast, that's key, isn't it? A fish store tank is like climate control for fish. Stable temperature, controlled light, regular feeding.
Everything managed.
But an outdoor pond, that's the Wild West.
Yeah.
You've got huge temperature swings, rain messing with the water chemistry, leaves falling in, debris.
And the big one.
Sunlight. Direct, intense sunlight.
Yeah, the complexity just skyrockets. The source makes it clear Ang understood this. If the coral rock actually provides a real benefit out there in that unstable mess,
Then it really proves its worth.
exactly, then it's not just something that works under perfect conditions.
Okay, so let's get into the why. Before we hit Ang's skepticism, what does the research mentioned in the notes actually claim this dried coral rock does? It looks like, well, just rock.
Yeah, it does, but the structure, that's the whole point. The research points to basically three main benefits, a sort of three-in-one deal.
Okay.
First function, and maybe the most obvious, is biological filtration.
Right, providing a home for beneficial bacteria. We need surface area for that. But why coral rock? Is it better than, say, those ceramic rings or lava rock people often use?
It's about the kind of surface area, porosity. Coral rock, because it used to be alive, has this incredibly complex structure. Think micropores and macropores, tiny tunnels, big tunnels, all interconnected.
So not just a flat surface, but like a sponge.
Kind of, yeah. But on a much finer scale and much more surface area packed into the same volume. It means it can hold way more bacteria per square inch compared to simpler media.
Ah, okay. So it can handle more fish waste, basically. More bioload. Less chance of the cycle crashing.
That's the idea. Especially useful in a store with lots of tanks and potentially high stocking levels. So, function one, it's a top-tier home for bacteria.
Got it. Superior biological engine. Makes sense. What's next? What about the other big headache in tanks, algae?
Function two is aimed at algae mitigation, and it supposedly does this through nutrient absorption.
How?
Well, the rock itself, its chemical makeup, calcium carbonate mainly, can pull excess nutrients out of the water. Things like nitrates and phosphates.
You're basically algae fuel.
Exactly. You starve the algae of nitrates and phosphates. They can't grow as easily, even if there's light.
Okay, that sounds pretty good, too. But hang on, this is where the source threw in a warning flag
Right.
about the outdoor pond.
Yes, precisely. Critical caveat. The notes say, look, this nutrient absorption probably works fine indoors where you control the lights. But they caution it might be much less effective outdoors in Ang's pond experiment.
Because of the sunlight.
Right. You've got this massive constant energy source, the sun driving algae growth. The rock might absorb some nutrients, but can it keep up when the sun is just relentlessly fueling photosynthesis?
Probably not. It's like trying to bail out a boat with a teaspoon during a hurricane.
Yeah, good analogy. The sheer potential for growth fueled by the sun could just overwhelm the rock's absorption capacity. Indoors, it might keep things polished. Outdoors, maybe not so much.
Okay, so function one, biofilter seems solid. Function two, nutrient control is questionable outdoors. What's the third angle? You said 3.
The third function connects directly to its chemical nature, the calcium carbonate. It's about pH stability, buffering.
Oh, okay. This is why saltwater folks use crushed coral and stuff, right?
Exactly. And it's relevant for some freshwater setups too, especially if you keep fish that like harder water or if your water source is very soft.
So how does it actually buffer? What's the mechanism?
It's pretty neat, actually. The normal process of breaking down fish waste, the nitrogen cycle, naturally produces acids.
Right, tends to lower the pH over time.
It does, and if the pH drops too low too fast, it stresses the fish, and it can even stall those beneficial bacteria we just talked about, a potential crash.
Okay.
The coral rock fights this. When the water becomes acidic, the calcium carbonate in the rock slowly dissolves.
Oh, interesting.
And when it dissolves, it releases carbonate and bicarbonate ions into the water. These ions chemically grab onto the acids, neutralizing them.
So it's like automatically adding buffer as needed. It reacts to the acid.
That's a good way to put it. It acts as a reservoir of buffering capacity, smoothing out those pH dips, keeping things stable.
Which seems really valuable for an outdoor pond, where, like we said, rain or big temperature shifts could cause sudden pH changes.
Yeah, absolutely. It provides that chemical resilience. So let's recap the theory. You've got great biological filtration, you've got some nutrient removal, and you've got vital pH buffering. On paper.
Sounds like a wonder material.
It really does.
Which naturally leads us to the twist. Because Ang, despite laying out all these research-backed benefits, wasn't convinced.
Not at all. This is where the source gets really juicy for critical thinking.
Ang says, point blank.
They write, and I'm quoting roughly here, "Nevertheless, I remain doubtful of this approach and wait and see the result in the coming days." Just leaves it hanging there.
Okay, why the doubt? It does 3 potentially great things, especially the pH buffering that seems like a clear win, especially outdoors. Why be skeptical?
That skepticism, that's really the core takeaway from this part of the notes. It forces you, the listener, the learner, to think about the practical realities versus the theory. We have to assume Ang's doubt isn't about the science being wrong, like, does coral rock buffer?
Yeah.
Yes. Does it have surface area? Yes. It's probably about the overall effectiveness in that specific challenging context.
Like, is it worth the trouble or the cost?
Exactly. That's one angle. Coral rock isn't always cheap, especially compared to standard filter media. Maybe Ang's thinking, I could use a sponge for bio, some Phosguard for phosphates, and maybe crushed oyster shell for pH, perhaps cheaper or more targeted.
So the rock tries to do 3 things okay-ish instead of using dedicated products that do one thing really well.
That could be part of the calculation. Is it efficient? But I think the bigger doubt ties back to that sunlight issue.
Function 2 failing?
Probably. Ang might be thinking, okay, function 3, the pH stability, that's likely solid. Function 1, biofiltration, probably decent too. But function 2, algae control. In this sun-blasted pond, it's almost certainly going to fail. I'm going to get pea soup algae bloom.
And if the main visual problem outdoors is often algae,
Then even if the pH is rock solid and the ammonia is 0, if the pond is an opaque green mess, is the technique really successful for that environment? The doubt is likely rooted in the expectation that the failure of the nutrient control function might outweigh the benefits of the other two.
so the environment dictates which function actually matters most. The theory is fine, but the sun changes the whole equation. Ang suspects the algae issue will make the whole thing impractical, despite the pH benefit.
That seems like the most logical reading of that skepticism.
Yeah.
The source ends right there, mid-thought, mid-experiment. It perfectly illustrates that theory is one thing, but real-world application, especially with uncontrolled variables, that's the real test.
Okay, that's a fantastic point. So pulling it all together for you listening, what are the key nuggets we've mined from Ang's notes here?
Well, first, the initial observation. That interesting fish store setup combining standard sponge filters with dried coral rock. An optimization strategy, maybe?
Yeah. Second, the 3 theoretical jobs of the coral rock. Top-tier biological filter surface, a chemical sponge for nutrients like nitrate and phosphate.
And a crucial pH buffer, stabilizing water chemistry.
But third, and this is the big one, the environmental caveat, direct sunlight, like in an outdoor pond, likely overwhelms the rock's ability to control nutrients, casting doubt on its overall effectiveness in that setting.
That context dependency is critical. What works indoors under controlled lights might not translate well when nature throws in curveballs like intense sun. You always have to evaluate based on the specific environment.
Right. Okay, that brings us towards the end of this dive, but let's leave you with a final thought, building on Ang's doubt.
Go for it.
Let's think about trade-offs. Imagine Aang does find the coral rock keeps the pond pH incredibly stable, much more stable than without it. Maybe it significantly reduces the time needed for water changes or chemical adjustments for pH. Even if the pond still gets choked with algae because the nutrient control part fails due to sun, could the rock still be considered worth it just for the pH stability benefit alone?
Interesting question.
Is the time and effort saved managing water chemistry worth the potential hassle of dealing with the green water aesthetically? It forces you to define what success actually means for your specific goals and your specific environment. What are you optimizing for?
That's the real question, isn't it? What problem are you actually trying to solve, and does the tool fit the job in that context? Keep testing, keep questioning.
Exactly. Calculate those trade-offs. We'll catch you on the next deep dive.